यही photo. In this module, module 4, we will talk about computer codes. And I am Get Willy from France, that is Paris. And today I am going to discuss about computer codes. In the previous lecture, we learnt about binary numbers, and in this lecture, we will learn about how binary numbers are coded to represent characters in computers. So, characters coding and scheme, also known as computer codes, are standards for representing characters in computers. They enable easy transfer, exchange of data between computers and between computers and peripheral devices connected to computers. They also enable independent development of several hardwares and software components for a wide variety of computers. Although many coding schemes have evolved over the years, we will discuss about below only the most commonly used computer codes. You see the natural beauty of this village and enjoying my lecture or lecture series, learning computer with seeing the natural beauty of Indian village. I think you have enjoyed very much. And now I am discussing about the computer codes. Next, see what I am going to talk about. This is the natural beauty of this village. You see, there is also building in this village. This is the high tension electric wire. You see, there are only trees and several types of trees. They are arranged in a regular pattern in this village. You see. Now come to the point. Numerical data is not the only form of data handled by computers. We often require to process alphanumeric data also. An alphanumeric data is a string of symbols where a symbol may be one of the letters A, B, capital A, B, C, dash, 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 Z, or on of the digit 0, 1, 2, 9 or a special character such as plus, equals, asterisk, slash, dot, uh, parenthesis, space or blank, etc. An alphanumeric data consists of only the letters A, B, C, dash, Z, and blank characters. Similarly, numeric data consists of only the digit 0, 1, 2, dash, 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 and 9. However, the bits 0 and 1 must represent any data internally. Hence, computers use binary coding schemes to represent data internally. In binary coding, a group of bits represents every symbol and appears in the data. The groups of bits used to represent a symbol is called a byte. To indicate the number of bits in a group, sometimes a byte is referred to as n-bit byte. For example, if we take 4 bit, then it will be called 4-bit byte. If we take 3 bit, then it will be called 3-bit byte, and so on. See the natural beauty of this village. In n-bit byte, here the group contains n bits. However, the term byte commonly means an 8-bit byte. That is, if generally we talk about byte, then this means that this byte contains only 8 bits in general, or a group of 8 bits, because most modern computers use 8 bits to represent a symbol. Now BCD code. Binary coded decimal. Binary coded decimal, it is also called BCD code, is one of the early computer codes. In BCD code, each digit of a decimal number is represented by its binary equivalent instead of converting the entire decimal values to a binary number. This makes the conversion process easier. In figure 4 point, there are several people walking on the road. In this village, they are going to for their work. You hear the sounds of some people, and some bikes are going from this road to the nearby town Sursand. Sursar or Susand? Sursand. Susand, nahi Sursand. People say that that town is Sursand. We talk about the BCD code, that binary coded decimal. Early computers uses this code, and in this BCD code, each digit of a decimal number is represented by its binary equivalent. Uh, Instead of converting the entire decimal values to a binary number, this makes the conversion process easier. We some BCD equivalent of decimal digit. For example, decimal digit is 0, and its BCD equivalent is reading from left to right. 0 0 0 0, that is 440, and the decimal digit is 1, and its BCD equivalent is 0001. Similarly, for 2, decimal digit 2, it is 0010, and for decimal digit 3, it is 0011. For decimal digit 4, BCD equivalent is 0100. BCD digit 5, BCD equivalent is 0101. Decimal digit 6, BCD equivalent is 0110. Decimal digit 7, BCD equivalent is 0111. And decimal digit 8, BCD equivalent is 100, as 1 after 30. And BCD decimal digit 9, its BCD equivalent is 1001. So we saw the different, we saw here 9 decimal digits in their binary equivalent, BCD, in the binary equivalent in BCD code. Since 8 and 9 requires 4 bits, so all decimal digits are represented in BCD by 4 bits. For example, we saw that 42 in decimal is equivalent to 101010 in binary. So converting 42 in decimal into BCD code, we produces the we have following results like 4 2 to the base 10 equals to, first we convert 4 into BCD code. The BCD code for 4 is 0100 and BCD code for 2 is 0010. After combining this, we get 01000010 in BCD. So similarly, we can make like this BCD code of other numbers. And now similarly see some another examples. For example, decimal number is 10 and its BCD code is for, so first we convert 1 and then in BCD code and then 0 in BCD code and then combine. The BCD code for 1 is 0001 and for 0 is 0000. That is, we have to take 4 bits for every digit in this coding system. And so BCD code of 10 will be 00010000. Similarly, for 15, we get BCD code for it 0001 and 0101. Thus, in our discussion, we have used a group of 4 bits to represent a digit character, which is called character. In BCD, 4 bits BCD coding systems can represent only decimal numbers because 4 bits are insufficient to represent the various characters used by a computer. Earlier I said that this is the place of great Indian Seth Jagbuk. Don't, I am sorry to say that that was not the full name of that saint. Whose full name was Jay Prasad Swargupta, and he was from second BC, not first BC. There was a ashram in this area around second BC, and in this side there was a huge pond dug by gods in Satyug. The people of this area said this. So this is the place of Jayaprasad Swargupt, who was a great saint in the second BC. Now let's come to the upper point. Hence, instead of using 4 bits with only 6 possible characters, computer designers commonly use 6 bits to represent characters in BCD code. 6-bit BCD code retains the 4 BCD numeric place position but adds 2 additional zone positions. With 6 bits, it is possible to represent 64, example 2 to the power 6, different characters, and this is sufficient to code the decimal digit 10, alphabetic letters 26, and other special characters 28. Special characters are 28. We have decimal digit 10 and alphabetic letters are 26 and other special characters are 28. Now we will see the example of coding of alphabetic and numeric characters in BCD code. Let's see some examples. Here are the some important codes. For example, character A and its in the previous lecture, we saw the use of octal and hexadecimal system as a shortcut notations for binaries. Since BCD is a 6-bit code, we can divide it easily into two 3-bit groups and use one octal digit for representing each of these 3-bit groups. Hence, computer professionals use octal number system as shortcut notation for memory dump in computers that use BCD code for internal representation of characters. This results in a 1 to 3 reduction in volume of memory dump. Now we see the octal equivalent of alphabetic and numeric characters coded in BCD. Here are some examples of BCD code or coded in BCD of characters and alphanumerics. For example, A, its zone value is 1 1 and digit BCD code the digit is 0 0 1 and its octal equivalent is 61 6 1. Similarly, character B have zone value 1 1, digit is binary digit BCD code is 0 0 1 0 and its octal equivalent is 62, and C zone 1 1, digit 0 0, that is binary digit 0 0 1 1, octal equivalent 63. Character D character D character D and its zone value is 1 1, digit is binary digit 0 1 0 0, octal equivalent 64. Character E zone 1 1, digit 0 1 0 1, octal equivalent 65. Similarly, for F, zone value is 1 1. Character is BCD code. Character value digit is 0 1 1 0. For E, 0 1 0 1 and 65. And for F, zone value is 1 1. Binary digit 0 1 1 0. This is the equivalent 66. Character G, zone value 1 1. Binary digit 0 1 1. Octal equivalent 67 or 67. Character H, zone value is 1 1. Binary digit 1 0 0 0. Octal equivalent 70. Character I, zone value 1 1. Digit 1 0 0 1. Octal equivalent 71. Similarly, we can write another value also. For example, character S. Now we see the character J. Character J. From J to R, the zone value will be 1 0. Zonal value will be 1 0. And we know the BCD code for J will be 0 0 0 1 and octal equivalent will be 4 1. For K, it is zone value is 1 0 and binary digit 0 0 1 0 and octal equivalent is 4 2. Similarly, for L, zone value is 10 and digit is 0011, octal equivalent 43. Similarly for M, zone value is 10, digit is 0101, octal equivalent is 45. And for O, it is zone value is 10, digit is 10110, and octal equivalent is 46. For P, digit is 0111, octal equivalent 47. For Q, we earlier said that from J to R, the zone value is same. So here only I talk about digit, binary digit. That is the BCD code for digit. For similarly for P0111 and octal equivalent is 47. Similarly for Q1000, octal equivalent is 50, and R1001, octal equivalent is 51. And from S to Z, zone value is 01, and then place digit value and then calculate octal equivalent. From S to Z, zone value is 01. So for character S, digit 0010, octal equivalent 22, and for T, digit 0011, octal equivalent 23. For U, digit 0100, octal equivalent 24. For V, digit 0101, octal equivalent 25 or 25. For W, digit 0110, octal equivalent 26. For X, digit 0111, octal equivalent 27. For Y, digit 1000, octal equivalent 30. For Z, zone is and for Z, the last group of this is Z, which zone is 01, and the digit is 1001, and the octal equivalent is 31. Now we see some example related to this. For example, write the binary digits. Binary digits used to record the word BASE in BCD. In the BCD binary notation, we know that B is represented by with its zonal value and BCD code. That is zonal value for B, zonal value is 11 and digit is 0010. So the code for B will be 110010. Similarly for S will be 010010, and for A will be 110001, and for E will be 110101. And combining this, hence we arrange like letters. We put uh, every code from left to right. For example, for B, it will be 110010. For A, 110001. For S, 010010, and for E, 110101. And so this, so in BCD code, the base will be recorded as 110010, 110001, 010010, 1101001. Similarly, we can see another example also. For example, in the next example, we see using octal notation, write the BCD coding for the word digit. Now, how word digit, that DIGIT, can be written in BCD coding, but you have to use octal notation. Now, in BCD octal notation, refer to in the earlier example, the octal equivalent of D is 64, and I is 71, T is 23, and G is 67. So arrange it. It is like as in the word digit. So for from left to right, for because we write digit, that is DIGIT. So code for D is 64, code for I is 71, code for G is 67, code for I is 71, and code for T is 23. So from this method we can convert any word into its BCD code representation or octal BCD representation, octal equivalent. Now our next topic is EBCDIC. EBCDIC. The major problem with BCD code is that it can represent only 64, that is 2 to the power 6 different characters. And this is not sufficient for providing decimal numbers 10, lowercase small letters 26, and uppercase capital letters 26, and a large number of other special characters 28 plus. Hence, computer researchers extended BCD code from a 6-bit code to an 8-bit code. They added 2 bits and are used as additional zone bits, expanding the zone to 4 bits. In the previous, there was zone of 2 bits, but in this case, the zone will be of 4 bits. The resulting code is called the extended binary coded decimal interchange code. Extended binary coded decimal interchange code. That is EBCDIC, extended binary coded decimal interchange code. And in this code, it is possible to represent 256, that is 2 to the power 8 different characters, instead of 64, 2 to the power 6. In addition to the various characters requirements mentioned above, this also allows a large variety of printable characters and several non-printable control characters. System designers enable use of control characters to control such activities as printer vertical spacing, movement of cursor on terminal screen, etc. Out of 256 possible combinations, several are still available for new characters assignment. Hence, the code can still grow as new requirements develop. And the code was developed by IBM, and the most IBM models use a EBCDIC code, that is extended binary coded decimal interchange code. Many other computers also use EBCDIC code. And now see the uh, some character used in this code and its value. For example, from A to I, the zone value will be 1100, and we put their corresponding digital value. That is, this is the digit value. For example, for A it will be the zone value is 1100 and digit value is 0001, and its hexadecimal equivalent is written as C1. Similarly for B, here the zone value for A to I is same. A to I not from zone. Yeah. From A to I, the zone value is same. Only digit change, digital value change, and its hexadecimal equivalent change. For example, A zone value is 1100, digit is 0001, and hexadecimal equivalent is C1. Similarly, for B, because zone will remain same, digit is 0010, hexadecimal equivalent C2. For C, digit is 0011, hexadecimal equivalent C3, and so on, like hexadecimal next will be C4, C5, C6, C7, C8 and C9, and the corresponding we have to put the digit value only to make this code. For example, the in EBCDIC code, the A character will be look like 11000001, and the value of H in this code will be 11001000, and hexadecimal equivalent CH, and so on. Now from J to R, the zone value is 1101. Now from J to R, all that is J, K, L, M, N, O, P, Q, R, all have same zone value 1101. Only digital value will be changed. This is the digit will be changed. For example, for J, digit value is 0001, 30 and 11, and for K, digit value is 0010, and for L, digit value is 0011, and similarly for another's, we know the digit value of all these letters. And its hexadecimal equivalent will start from D1 and from D1 and end at D9, that is D1, D2, D3, D4, D5, D6, D7, D8, D9. Now, beautiful. Now again the character from S to Z, that is STUVWXYZ. The zonal in EBCD code zone value is 1110, that is 3, 1 and 1 0 for every character from S to Z, and the corresponding digit we have to put only corresponding digit. For S it is 0010, and for Z it is 1001, and for T it is 0011, for U it is 0100, for V it is 0101, for W it is 0110, for X it is 0111, for Y it is 1000, and similarly. And the hexadecimal equivalent starts from E2 to E9. That is, for S it is E2, for T it is E3, for U it is E4, for V it is E5, for W it is E6, for X it is E7, for Y it is E8, and for Z it is E9. So see, we have seen here the uh, character EBCD code of characters A to Z. Now we see the EBCD code of digit 0 to 9. For the digit 0 to 9, the zone value will be 1111, that is 41, and it will be from 0 to 9. For every digit, that is for 1 it is also 1111, for 2 it is also 1111, and the corresponding digit will be same. For example, for 0 it is 0000, that is 40, because we make 4 bit in BCD code we use 4 bit. And for 1 it is 0001, for 2 it is 0010, for 3 it is 0011, for 4 it is 0100, for 5 it is 0101, for 6 it is 01110, for 7 it is 0111, for 8 it is 1000, for 9 it is 1001, and the hexadecimal equivalent is from F0 to F9. For example, for 0 it is F0, and for 9 it is F9, or for 1 it is F1, for 2 it is F2, for 3 it is F3, for 4 it is F4, for 5 it is F5, and for 6 it is F6, for 7 it is F7, and for 8 it is for F it is F8, and for 9 it is F9. So I think you have enjoyed my lecture series, learning computer with seeing the natural sites, beautiful sites, that is natural beautiful sites of village, Indian village, not European or American village. I am showing you the sites of only Indian village.